Good morning, students. Today we are going to see the experimental determination of specific conductance and equivalent conductance. The specific conductance and equivalence conductance are determined with the help of potentiometer. This is the diagram of potentiometer. In this diagram, we clear cut see that resistance box is placed on left gap or left hand side, while on right hand side a conductivity cell with a solution of electrolyte is placed. This conductivity cell contains two platinum electrode having area of cross section a centimeter square, while distance between these two electrode it is L centimeter. This is the galvanometer and it is the potentiometer wire. Now what happens when electric current is flow through the solution? When electric supply is on, a current flows to the circuit. Resistance R is taken out from resistance box such that when jockey is placed near a point A and point B on potentiometer wire, galvanometer should show deflection in opposite direction. Then jockey is moved on the wire and point at which null deflection is obtained is recorded. What is the meaning of null deflection? It show galvanometer should show 0 reading. That point we have to find on potentiometer wire. Let the point be O. So just see in this diagram, when the current is flowing through the system, we have to move jockey on this potentiometer wire so that galvanometer should show 0 reading. So let that point be this. It is point O. If R is the resistance in the resistance box and X is the resistance of the solution, so R by X is equal to length of OA divided by length of OB. So basically a principle of Wheatstone bridge is used here. So one can simply write from this formula X is equal to R multiplied by length of OA divided by length of OB divided by length of OA. So conductance, that is capital C, is equal to 1 by X. We know that specific conductance is related to observed conductance. So K, that is specific conductance, this is the small k. Always remember specific conductance is shown by small k. So small k is equal to observed conductance multiplied by L by A, where L is the separation between two platinum plates or electrode in conductivity cell and A is the cross section area of the plates. This ratio, that is L by A, is called cell constant. So we can simply write specific conductance K is equal to conductance, that is observed conductance C, multiplied by cell constant, that is L by A. If a concentration of a solution is known, then we can calculate equivalent conductance using the equation lambda is equal to K divided by C, or lambda is equal to K multiplied by 1000 divided by normality. So now just see cell constant and its determination. The resistance of any conductance is directly proportional to length of conductor, and it is inversely proportional to cross section area of that conductor. So we simply write resistance is directly proportional to length of conductor, and it is inversely proportional to area of cross section. So R is equal to rho multiplied by L by A. So 1 by R can be written as 1 by rho, and inverse of this quantity, that is A by L. So observe conductance 1 by R, that is reciprocal of resistance, is conductance. So conductance is equal to, what is rho stands for? It is specific resistance. So inverse of specific resistance is specific conductance. So conductance is equal to specific conductance multiplied by A by L. So one can write specific conductance is equal to observed conductance multiplied by L by A. Just see this quantity get inverse here. So the factor L by A varies from cell to one cell to other cell, and it is called as cell constant. It is the important. It is given by cell constant is equal to specific conductance divided by observed conductance. So this quantity is known as cell constant, and it is simply written as, it is the ratio of specific conductance to that of your observed conductance. Now we are going to solve some numericals. So in this numerical, a cell is deep in 0.1 normal KCl, shows the resistance 120 ohm. Calculate the cell constant if specific conductance of 0.1 normal KCl is 1.12 Siemens meter inverse. So specific conductance value is given, that is 1.12 Siemens meter inverse, and resistance value is also given, that is R is equal to 120 ohm. We know that cell constant is equal to specific conductance divided by observed conductance, and reciprocal of resistance is conductance. So we going to calculate observed conductance from this resistance value. So observed conductance C is equal to 1 by R, that is 1 divided by 120. It comes as 8.33 multiplied by 10 raised to the power minus 3 Siemens. Just put value of specific conductance and observed conductance in this formula. We comes with cell constant value. It comes as 1.344 multiplied by 10 raised to the power 2 meter inverse. In second numerical, the resistance of 0.5 normal solution of an electrolyte is 45 ohm. Calculate equivalent conductance if the electrodes of a cell are 2.2 cm apart and have cross sectional area 3.8 cm square. So value of R is given, that is 45 ohm. Concentration is also given, that is equal to 0.5 normal. Just convert this normality into equal DMQ, equivalence DMQ. So it is 0.5 equivalence DMQ. Now just it is important to convert this DMQ into into meter cube. So for conversion of DMQ into meter inverse cube, we have to multiply this quantity by 1000. So 0.5 equivalence DMQ, this is always equal to 500 equivalence meter inverse cube. Just value of L is given, that is length of that is length between, that is separation between electrodes are given, that is L is equal to 2.2 centimeter. Convert this centimeter into meter. Just multiply this with 10 raised to the power minus 2. Area of cross section is always also given, that is 3.8 centimeter square. Convert this centimeter square into meter square by multiplying 3.8 with 10 raised to the power minus 4. So, and we have to calculate equivalence conductance. We know that equivalence conductance is equal to K divided by C. So, first we have to calculate C, that is conductance 1 by R is equal to 1 divided by 45, which comes as 2.22 multiplied by 10 raised to the power minus 2 Siemens. Now, don't confuse this C with this C. It is capital C for conductance. It is the small c for concentration. So, we know that specific conductance is equal to observed conductance multiplied by cell constant. So, small k, that is specific conductance, is equal to capital C multiplied by L by A. We have all the values. Just put all the values in the formula. We comes with specific conductance, that is 1.286 Siemens meter inverse. Equivalence conductance is equal to specific conductance divided by concentration. Don't confuse this small c with capital C. Capital C stands for conductance, small c stands for concentration. So, concentration of solution, that is small c, it is equal to 500 equivalence meter inverse cube. So, 1.286 divided by 500. When we solve this, we comes with 25.72 multiplied by 10 raised to the power minus 4 Siemens meter square equivalence inverse. Now we are going to solve third numerical. The conductivity of 0.199 molar, it is important, solution of KCl is 2.479 Siemens meter inverse. Calculate its molar conductivity at this temperature. So, concentration small c, it is given 0.199 meter, not meter, it is mole. So, just convert this into mole dm inverse cube or dm mole per dm cube. So, multiply this quantity. Now, convert this per dm cube into per meter cube. So, multiply this quantity with 1000. So, concentration of KCl is 199 mole per meter cube. Specific conductance is given, that is 2.479 Siemens per meter. So, K is equal to 2.479 Siemens per meter. So, we know that molar conductance is equal to specific conductance divided by concentration. It's important, if this concentration term is given in molar, then this quantity is molar conductance. If concentration is given in normal, then it is known as equivalence conductance. We know that this C is given in moles. So, K is equal to K divided by C. Just put all the values here. and solid. So we comes with molar conductance is equal to 1.24 multiplied by 10 raised to the power minus 2 Siemens meter square per mole. The resistance of 0.1 molar KCl solution in a conductivity cell is 325 ohm, and the specific conductance of the same solution is 1.29 Siemens per meter. If the resistance of 0.05 mole NaCl solution in a same cell is 752.4 ohm, calculate the equivalence conductance of NaCl solution. Now, for KCl solution, specific conductance value is 1.29 Siemens per meter, which is given. Resistance is also given, which is 322 ohm. So we can calculate conductance by this quantity, that is conductance is equal to 1 by R. So that is equal to 1 by 325, which comes as 3.077 multiplied by 10 raised to the power minus 3 Siemens. We know that cell constant is equal to specific conductance divided by observed conductance. So cell constant, we know value of K and value of observed conductance, which is calculated. So put both the values here in this formula. So cell constant comes as 419 meter inverse. Now for NaCl solution, concentration is given 0.05 mole. Convert this into equivalence per meter cube. So first we have to convert it into dm cube. So mole is equal to 0.05 equivalent dm cube per dm cube. Multiply this quantity for conversion of this dm cube into meter cube. Multiply this quantity with 1000. Value of R is given, that is 752.4 ohm. So we know that R is equal to 1 by C. So 1 divided by this, C is equal to 1 by R. So that is equal to 1 divided by 752.4. So conductance is equal to 1.329 into 10 raised to the power minus 3 Siemens. Now we know that K, that is specific conductance, is equal to observed conductance multiplied by cell constant. So we got the value of observed conductance for NaCl solution, and we calculate value of cell constant, that is 419 meter inverse. So put all the values here, we comes with value of specific conductance, that is 0.557 Siemens per meter. For calculating equivalence conductance of NaCl, we have a formula, that is equivalence conductance is equal to specific conductance divided by concentration. So value of specific conductance for NaCl solution is first calculated, which is 0.557 Siemens per meter, and concentration of NaCl is given, that is 50 equivalence per meter cube to divide by 50. After solving this, we comes with 1.114 multiplied by 10 raised to the power minus 2 Siemens meter square per equivalence. In our next class, we are start with RNS theory of ionization. Thank you very much.